So yes, I'm from the Open University and I'm talking about Mercury. There's a nice, colourful looking view of Mercury on the screen there. It's not that colourful unless you work quite hard to improve the images, but that's the level of detail that we can see from spacecraft. Well, we can see much closer in there from spacecraft, as you will see. But Mercury, when I was a lad, it was quite a boring planet. We knew nothing about it, and it was small and close to the sun. And we're still very puzzled by it. A colleague of mine has described it as the problem child of the solar system. This is Jack Wright, who is about to start working for the European Space Agency on this planet, because it doesn't particularly fit. It's the closest planet to the sun, and it's rather anomalous. But it is a terrestrial planet. It is a rocky planet. That's what we mean by a terrestrial planet. Here's a view of the solar system from a long way above, and you see the outermost real planet Neptune, and then here's the orbit of Jupiter, and the rocky planets are confined in this inner zone here. So let's zoom into that. Here's the inner solar system as it is right now. This is dated today's date, and Venus is between the Earth and the Sun, and Mercury in this orbit here is even closer. Here's the Earth right now. There's Mercury right now. Mercury would be in the morning sky if you got up before dawn and it was clear. Now, the solar system only has 4 rocky planets, but there's also the Earth's moon, which in terms of its characteristics is like a rocky planet. This one is Mercury. Here are all the others, and you will see that Mercury on the left there is bigger than the Earth's moon, but smaller than Mars. So it's the smallest of the 4 terrestrial planets, but it's somewhat bigger than the moon, which is a very similar looking body. And these are all bodies that have rock on the outside and probably cores of mostly just iron in the middle. They're too dense to be rock all the way through. Just comparing the Earth-Moon system with Mercury, Mercury is only 58 million kilometers from the sun, whereas the Earth is 150 million kilometers from the sun. So Mercury is 3 times closer to the sun than the Earth is. So, I mean, just ponder a moment. This isn't an official poll, but how much stronger do you think the sunlight would be at Mercury than it is at the Earth? If you're 3 times closer to the sun, how much stronger is the sunlight? I'll just let you ponder that before I hit the answer. There are a couple of polls coming up later where you can vote. But actually the answer here, if you're 3 times closer, it's 3 squared times more sunlight. The sunlight is 9 times stronger at Mercury than the sun. So per unit area on Mercury, you get 9 times more solar heating than you do on the Earth. And the effect of this is that Mercury's surface is very hot. It's up to 430 degrees centigrade by day. But the planet has no atmosphere, and at night it loses its heat by radiation to space very efficiently, and the temperature can drop to minus 180 centigrade at night. So that's a range of 600 degrees between hottest and coldest, between noon and midnight. So it's a planet of extremes. Now, Mercury takes 88 Earth days to go around the sun. And what shape orbit does it travel around the sun in? Well, you probably know that all planets travel in elliptical orbits. They're not circles, they're ellipses, but they're pretty close approximations to circles. They're not strongly elliptical, but Mercury's orbit is the least close to a circle of all of them. It's the most strongly elliptical, or if you like, the most eccentric orbit. Here's a zoom in on that graphic you saw before, showing Mercury's orbit around the sun. And this is the closest point in Mercury's orbit to the sun. And that's where it's experiencing the strongest gravitational pull from the sun. So that's where it moves fastest. And this opposite point, the far point in its orbit, is where it's furthest from the sun, weakest pull from the solar gravity, so it moves slowest. So its speed varies as it goes around the orbit. Now, it takes 88 Earth days to go around the sun, and it actually takes 58 and nearly 3/4 days to spin once on its axis. So I've got a question for you here. Well, this actually works out to exactly 3 rotations per 2 orbits. I mean, this times 3 isn't exactly 176, but we've done some approximations in these figures, but it's exact. The 3 rotations of Mercury is exactly the time it takes to go around the sun twice. So it makes 3 rotations in exactly 2 orbits, or 2 of its years. So my question for you, and this is a poll question, if Megan can put the poll up, how many Mercury days are there in a Mercury year? Is there half a day, 1 day, 1.5 days, or 2 Mercury days in a Mercury year? So let's have some votes. I can see the poll filling up here. 3 rotations per 2 years, or per 2 orbits. How many days in a year? Okay, well, I think the polling has settled down now. And 78% of you have said there's 1.5 days in a Mercury year. And you're fairly evenly split over the others. Okay, thank you for that. We'll stop that poll and I'll move on to my next slide if I can. Or there's the options I already gave you. And try and move on to the correct answer. There's only half a day in a Mercury year. Mercury's day, sunrise to sunrise, is twice as long as its year. Let me show you a video here which explains it. If I can set it running. Here we go.
"60-second adventures in astronomy. Number 4, a day on Mercury. No 2 planets act exactly the same, whether it's Jupiter spinning in only 10 hours, Venus spinning backwards, or Uranus tilting to one side. But Mercury is particularly strange. It takes nearly 59 Earth days to rotate, which might make for a pretty long day, but at least you'd have time to get things done. But while the days are long on Mercury, the years are relatively short. It travels round the sun in just 88 Earth days. Now, until 1965, we thought Mercury span exactly once per orbit, which would mean that one side of it was always facing the sun. If it spanned twice every orbit, its day would be the same length as its year, which would at least make calendars nice and simple. But it actually spins 3 times for every 2 orbits, which means each Mercury day lasts for 2 Mercury years. So while you might get a bit bored waiting for the evening, at least you'll be able to celebrate your birthday twice a day, even if you had to share it with everyone else.
Okay, well, I don't know if that helped clarify things for you or not, but the point is, if you rotate exactly once per orbit, you'd be keeping the sun fixed in your sky. Because Mercury rotates 3 times in every 2 orbits, it takes 2 orbits to complete a day, sunrise to sunrise. Its day is twice as long as its year. That partly explains the extreme temperature ranges. It stays daylight for a long time and night for quite a long time, so it can heat up and cool down quite a lot. Let's take a peek inside Mercury. This is the Earth and Mercury at the correct relative sizes. You see Mercury is smaller than the Earth. Let's bring Mercury down and open it out. This is what we're pretty sure Mercury is like inside. There's the inner core here, which is solid iron. There's the outer core, which has got to be liquid iron. It's churning around because it generates, we know this because it generates a magnetic field, which we've measured with spacecraft. You can't have solid iron generating a magnetic field inside a planet. It's too hot. It can't act as a permanent magnet. You have to have an electrical conductor that's churning around, convecting, or some other kind of motion to generate the magnetic field. Then there's this rocky mantle and quite a thin, rocky crust. The Earth has crust, mantle, and outer and inner cores as well. But the balance between these is much different on Mercury. Here are the four rocky planets and the moon, showing their core sizes. Mercury's core, inner plus outer core, makes 58% of its volume, which is a much greater percentage than the Earth's or any of the other bodies' cores. Mercury has an enormous core. We can tell this from its density. It's just too dense to have as much rock and as little iron as the Earth does. It's a very large core relative to its size. So how do you get that? Well, this goes back to the processes involved in Mercury's birth. This is an artist's impression of two young planets or planetary embryos colliding. Well, what happens in a collision like that? Well, let's just take a peek inside them. Let's assume these are hot enough that they've differentiated, but the dense iron has sunk inwards to form the core. So the core is the red stuff, and the less dense rock is on the outside, forming the mantle and the crust. What happens in this collision between these two bodies that are differentiated with an iron core and a rocky mantle and crust? It depends on how they collide. If it's a head-on collision like that, you can get merger between the two bodies, and you just get an agglomeration of the two. But what happens if the collision is oblique, like this? It turns out that in that condition, they don't usually merge. What happens is the small one can be stripped of a lot of its rock, which will join the larger body, whereas the smaller body down here hasn't had its core much affected, but it's reduced in its amount of rock. So this target body, the big body, has gained some rock, and that could eventually become the Earth or Venus. And this thing down here that's lost a lot of rock could become Mercury. So it may be an oblique collision towards the end of the planet building process, but left us with this body that we now call Mercury. Lost a lot of its rock, which is why its core is relatively so big. And that's a neat explanation, but it turns out the rock that we see on Mercury is kind of hard to explain as a result of this, because I'm jumping ahead now, but Mercury's rock is quite rich in volatile elements, things like sulfur and chlorine, which you'd expect to have been lost preferentially in a very violent collision. So we still don't understand Mercury's birth, but this is perhaps the best way to explain it. Now let's turn to a little bit of Mercury's geology. Here's an oblique view across Mercury. Most of the views I'll show you are looking obliquely across Mercury. You see, it's a cratered world. Craters you get on planetary bodies because cosmic debris, bits of asteroid, bits of comet are hitting the surface at several tens of kilometers per second. And when that happens, they make an impact crater because of the shock waves. Because of the speed of a near instantaneous impact, it excavates these craters. And craters don't get eroded away on Mercury. There's no atmosphere. We think there never has been. So some of these craters on Mercury go back for billions of years. Around here, there's a degraded crater that's billions of years old. This is a much fresher looking one here, and some even fresher, relatively young craters here. And there's a crater here that's got a ring of peaks in the middle, and there's its outer rim here. Let's just pan up towards the horizon, and there's the edge of the globe. I really love this view. It's what you'd see if you were orbiting Mercury, looking out of the window of your spacecraft. It's a fascinating world, and you might think, oh, this looks just like the moon, and in many respects it does. But the nature of the rocks, the chemistry of the rocks is a little bit different. How do we know about Mercury from spacecraft? There have been only 3 missions. The first one here is Mariner 10, which had 3 flybys of Mercury. It didn't go into orbit in 1973 and 1974. That's the spacecraft which discovered the magnetic field around the planet, which told us its core was fluid, churning around to generate a magnetic field. That was a big surprise. It wasn't expected. The next spacecraft was called Messenger. Here it is being launched on the right, and an artist's impression of it in orbit about the planet on the left. This had a successful orbit of a planet which lasted 4 and a bit years, 2011 till 2015. And all the images of Mercury I'm going to be showing you are from Messenger. Then there's Bepi Colombo. This is a joint mission between the European Space Agency, ESA, and the Japanese Space Agency, JAXA. That's on its way. We've got a flyby of Venus coming up later in this year, then some Mercury flybys. We don't get into orbit about Mercury and start sending back science data until 2026. It's quite a slow process, getting to Mercury so you can get into orbit. And when we do get there, we release this Japanese spacecraft here, and then this European spacecraft here is able to do its own science, and we start getting some really wonderful science from this. There's one UK-built instrument on board. It's MIX, the Mercury Imaging X-ray Spectrometer, masterminded from Leicester University, and this will measure X-rays fluoresced off Mercury's surface, and that will allow us to measure the abundances of the chemical elements, to map the abundances of the chemical elements, to help us understand the rock types better. If you want to see Bepi Colombo, when we can start visiting places again, there is a full-size replica of it in the Science Museum in London. That's me for scale. It's a pretty substantial spacecraft. And MIX, the British instrument on board, is here. This is an engineering copy of it at Leicester University, and that's me behind the mask. That's pre-COVID days. I'm wearing clean room suits and masks and gloves to stop me getting any bodily particles onto the equipment there, because these things you want to keep as clean as you can. And this is a lens which collects the X-rays and focuses them onto the focal plane assembly down there. So that's a very nice instrument, one of many on the spacecraft. No instrument on its own will give the answers to the questions that we're seeking, but in combination, we hope to learn a lot more about Mercury. So let's take a look at it as a geological body now. Here's a view just in black and white, and you might notice it doesn't have the strong contrast between the dark areas and the bright areas that you might see on the moon. It doesn't have large areas rich in crust that's floated to the surface, feldspar crystals which form the bright areas on the moon. Mercury is all pretty dark. It's as dark as the dark areas on the moon. The brightest patches are the youngest impact craters, which have yet to fade into the background. There is color. Here's a color view of the planet. It's false color, but it's like an exaggerated version of the true colors. I'm going to call up a globe which we can set rotating. If I can find the button that sets it rotating. There goes the globe rotating around. And what I want to point out to you, this is the largest impact basin on the planet, flooded by orange colored lavas. The orange lava's up near the North Pole as well. And we'll look at these orange colored lavas very soon. Let's rotate that globe around once more time. You'll see young impact craters that look bright and have got rays radiating from them. Another orange patch of lavas there. This is that big Chloris basin I mentioned, I pointed out before, that's filled with orange colored lavas. So there's a globe with some color variations on it, and we'll look for some more details as I progress the talk. To go on to the next slide. Here's a global view, kind of unwrapped. On the right here, this is Chloris Basin, the biggest impact basin on the planet, filled with orange lavas. It's just over 1,500 kilometers across. There are also some young, generally orange lavas near the North Polar region. I'm going to show you an image of this kind of region here very shortly. But just on the side, Megan mentioned I'm involved in a European Research Council, European Union, basically, project for mapping Mercury. Here's one of the maps that we produced of a region in the Northern Hemisphere. That was the image of it. Here's the geological map we've made. And we're trying to get the whole planet mapped like this so we can set the context for the observations that we'll be making with Bepi Colombo. And then Bepi Colombo will help us make a whole new generation of maps, and these will become obsolete. But all this sort of salmon pink color up here is the youngest lavas that were mostly in that orange color on the previous images. So let's look at these orangey lavas here. This is not strongly exaggerated color. You might see a slight orange tint, but the younger lavas are all here, and this is older terrain down the left and the bottom. So that's down the west and the south part of the image. Now, this is probably lava terrain as well, but it's older and has therefore accumulated more impact craters. We can tell that this region up here in the upper right is lavas because of hints lying within the image data. The surface is quite wrinkled. We call these features wrinkle ridges. I'll trace a wrinkle ridge here, for example. Those typically develop in lava fields. You see them on the moon as well. But I'm going to focus in on this area up here inside that little box. And I'll move on to the next slide. And hopefully you can see a sort of large circle feature. It's about, you see the scale bar, the whole circle is about 30 kilometers across. I'll trace the rim of the circle. So that's the rim of the circle. That's, we think, the buried rim of a crater. And you see there's a kind of radial pattern of cracks inside the crater. This is all lavas, but the crater was there on the surface that was covered by the lava, and the crater was completely hidden by the lava. But we can now see traces of it for reasons I'll explain. And all these smaller circular holes are craters which have formed after the lava had solidified. This is what we call a ghost crater. And really the only way to bury a crater is with lavas. What we can think of is to bury it with lava. So we're pretty confident we're dealing with lavas here. So let's take a look at this crater in cross sections. Here's a cross-sectional view through Mercury. A crater 30 kilometers across on Mercury in cross section would have had a central peak on its floor, which would be much lower than the crater rim. Okay, now let's flood this with lavas. We'll erupt some lavas to a sufficient depth to overtop the rim and to completely hide the crater. So that crater is invisible, but notice the rim is not very far below the surface. If we just wait while that lava cools down, it will contract a little bit thermally. And probably just as importantly, we'll have gas pockets within it, gas bubbles and larger blisters of gas. And these will be compressed under the weight of the lava. So the surface will sag, will subside a little bit, like so. And now I hope you can imagine, if you looked at that above, you would see the buried trace of the crater rim. You wouldn't see the central peak, it's too deeply buried, but you might see some radial cracking in here. And that's just what we see in that ghost crater. So the presence of these ghost craters is very strong evidence that we've flooded the terrain by lavas. So that's the effusive volcanism on Mercury. Most of these large lava plains ceased to be in place sometime between 3.5 and 3 billion years ago. There's been no widespread lava eruptions throughout the most recent 3/4 of Mercury's history. Let's look at another kind of volcanism. This is the whole of the Caloris Basin. You might remember I showed you that on the rotating globe. Here's the edge of the basin around here. It's occupied by orange-colored lavas, but there's some even more strongly orange material there inside this circle here, down near the southern rim. And in this area here, and I'm going to go into that box and show you that example. And we think these diffuse orange patches are even younger than the lava eruptions, and they are products of explosive volcanic eruptions. So here's within that square there, close up of that area, or high resolution view of that area. There are many circular impact craters, which I'm not interested in here. There's one there. There's another one there. But there's a hole in the ground there that is very far from circular, and it's surrounded by this more strongly orange or brighter orange deposit, which fades out towards the edge. And it's about 50 kilometers from side to side. And we think what we're seeing there is in the middle, a hole in the ground blasted by an explosive volcanic eruption. And the diffuse deposit is the stuff that's been thrown out by that eruption. Now, we don't see any eruptions going on Mercury today, but we do see very similar eruptions happening on a moon of Jupiter called Io. And here's a little video sequence returned by New Horizons. That's a probe which went past Pluto 4 or 5 years ago now. And you see what's happening just slightly on the far side of the globe, there's an explosive eruption throwing stuff out, which is falling back to the ground on these parabolic trajectories. We call that an umbrella plume. This wouldn't happen on the Earth. A volcanic explosion that goes high in the sky will entrain the Earth's atmosphere and give you a big convecting column. But on a planet with no atmosphere, there's no gas to entrain, and the particles, there's no atmosphere to entrain, and the particles thrown out by the explosion will just follow parabolic trajectories and give you these umbrella plumes. And so when they hit the ground, they form this diffuse deposit. So that's the explosive deposit. And if you look inside the hole in the ground, in really high resolution images, you see it's quite a complex feature. This end of it is old enough to have had quite a few impact craters form on it. These depressions in the ground at the other end have got almost no impact craters. There's one impact crater there and another one here, but it's less cratered than this end. And the middle part, there's several discrete holes in the ground, which are looking quite rugged. They're probably the youngest features there. What we think's gone on is the first eruption was here, the next was here, the next was there, and maybe here and here, and the youngest one's somewhere like this. And that's about 9 eruptions in total contributing to this diffuse deposit around a vent. So that's explosive volcanism from vents which are active many times in slightly different positions, and maybe over quite a long time scale, because the difference in cratering and texture indicates, to me at least, that this is quite an old end, this is kind of middling in age, and this is the youngest part of the vent. So explosive eruptions, younger than the lava eruptions, happening multiple times. And there are over 100 explosive volcanoes recognized on Mercury like this. And what they tell us is that Mercury is rich in volatiles, or stuff that will turn to gas. An explosive eruption is caused to be explosive because the magma, the molten rock rising upwards, has got gas dissolved in it, which comes out of solution sufficiently violently to blow the magma to smithereens. That's what volcanic ash is. It's just fragmented magma. So you've got gas-rich magma coming to the surface in Mercury, a planet that's close to the sun, violent birth. You don't expect it to be rich in volatile stuff that will turn into gas, but it clearly is because of all these volcanic vents which have erupted explosively. And the youngest of these might be only a few tens of millions of years old. Most of it is older, but some of it might have continued into the relatively recent past. One other piece of visual evidence for Mercury being rich in volatile elements, which I repeat, we didn't expect that close to the sun, comes from something called hollows. Now here's a peak ring base, and there's the inner ring of a crater. There's the outer edge of it. It's got a smooth floor. It's been flooded by lavas. Here's some quite large, more recent craters. You might see these radial cracks where the lava subsided under its own weight. But what I want to draw your attention to is on the peak ring, this kind of bright mottled texture. Let's look at that in color. There's a color image superimposed. Let's blow that up. This is what we see. You've got a red surface here and these areas which look bluer. And if you look closely and bear in mind that on this view, the sunlight is shining from left to right, what we're seeing here is steep-sided, flat-bottom depressions in the terrain. This is perhaps the clearest one. This dark blue floor surrounded by a bright blue halo is lower than the red material all around it. What's happened is you've stripped away the red material to expose the blue material. Now, how is that going on? And also, when did it go on? Well, the when did it go on is easier to answer, because if you look at this, you will not see any impact craters superimposed on these hollows. These hollows are young. They're probably active today. They might be widening at the rate of a millimeter every 1,000 years or something. It's not a fast process, but it's going on today. The surface is being stripped away. Now, how can that happen on a planet with no atmosphere? Here's a closer view I should have showed you. Do you believe me now? These are steep-sided, flat-bottom depressions. They're maybe 20 meters deep, They're hundreds of meters wide and their edges are steep. A really weird texture that we did not expect to see on Mercury. Let's see this in cross section. So what I'm showing here is it's a sun shining in the sky. Here's a cross section through Mercury's surface. The top 20 meters or so is the red stuff, the blue stuff below it. Well, somehow, probably because the sun is so strong, it's beating down on the surface, something from the sun is attacking the surface and causing the surface material to volatilize, to turn to vapor or to turn to atoms and be lost away to space. We think stuff is being lost to space here. It's not wind blowing it away. It's not falling into some underground chasm. We think that molecule by molecule, it's being lost to space. Now, how does the effect of the sun do this? Well, it could be the heat. It could be breaking chemical bonds because it gets so hot at day, almost 500 centigrade. It could be charged particles from the sun, cosmic rays reaching the surface, which despite the planet's magnetic field, they will do sometimes. Or it could be photons from the sun, ultraviolet photons breaking chemical bonds. But somehow the sunlight is attacking the surface. And as the stuff is lost to space, it eats down, eats all the way through the red layer. When it gets right through the red layer, all it can then do, because the blue stuff is not volatile, is just these hollows will widen. So the hollows widen like this, and then locally, for some reason, they cease, and we see these vast, extensive fields of hollows today. So if something is volatile in Mercury's surface, we don't know the process that volatilizes it, but we suspect the sun is involved in it, and we don't know what is being lost. When we get Bepi Colombo there, if we can measure the difference between this stuff, the pink stuff, and the blue stuff that's exposed in the hollows, maybe we'll have a better clue as to why hollows are growing. But we're pretty sure it's more evidence that Mercury is rich in volatile elements. And we do know from the X-ray spectrometer a messenger took to Mercury that the surface is rich in sulfur. There's between 2 and 4% sulfur wherever you look. Now, we don't think it's this red layer is pure sulfur. It might be a sulfide. It might be calcium sulfide, magnesium sulfide that's there available to be broken down. But basically, we've got very little evidence, which is why we're so glad we've got Bepi Colombo on the way there. Okay, final thing about Mercury I want to talk about before I finish is that Mercury is shrinking. There you go. Well, it's not shrinking that dramatically. Its radius has shrunk, we think, by about 7 kilometers in the past 3 billion years. And here's the evidence for that. This is an oblique view that's colored by altitude. And I hope you can see there's a fault, a thrust fault for a geologist running across this view. There's an escarpment. Where's my cursor? There's an escarpment running across the ground here. This is where a fault cuts up towards the surface. You see it runs through this younger crater here, and indeed this much bigger, older crater here. The fault cuts through all these craters, but this crater might be younger than the faulting. So let's see a cross-section of that. This is what we think we're looking at. A thrust fault below the ground. The terrain on the left, the terrain on the left is being shoved over the terrain on the right, producing this low-baked scarp. And you can see it cuts through the crater. And if you can measure how much the crater's been shortened, you can measure how much movement there's been on the thrust. Let me just go back so you can relate this block diagram to that view. Hope you believe me, that looks like a thrust fault reaching the surface. And because Mercury is cooling down, it's contracting thermally, and we think that's what's driving the thrust movements which displace the surface like this. Let me show you some evidence of that on Mercury. I'm going to go to this area here, and there's this arc-shaped feature here, which is named Beagle Rupees. Here are the lines that geologists would draw showing where the faults reach the surface. So the terrain on the left is being pushed over the terrain on the right, relative sideways motion, where the fault bends round, and pure compressive motion at the front. And I'm going to zoom into this region here. Where's my little box? Okay, there's a block diagram of what we think is going on. sheet on the right being pushed over the sheet on the left. Let's go into this box at the front of the fault. And what you see depends on where the sun is in the sky. With the sun from right to left casting shadows, you can see that this crater here, or is this the edge of a crater? Has it been shortened by this bit of thrusting? Certainly we haven't got a complete crater there, have we? So we'd say this crater here is older than the thrust movement. If we get a high resolution image of the sun higher in the sky, there's a scale 20 kilometers, by the way. Let's see it with the sun higher in the sky. Oh, now we can see there's a crater here which is younger than the thrust movement, whereas this is clearly older than the thrust movement. So if we knew the ages of these two craters, which we don't, we could bracket the age of the thrust movement somewhere in between the two. And you can measure the movement on this thrust, and it's moved by about 2 or 3 kilometers, which is not a lot. Thrusts on the Earth have moved by a lot more than that in some examples, but we've got these thrusts all over Mercury, accommodating the global shrinking as the planet contracts thermally. So I'm going to wind up by showing you this thrust scarp here. It's called Calypso Rupes. You can see the escarpment here. This is the front of the thrust feature. It's got some interesting steps in it. But I've got a question for you, which is Calypso Rupes older or younger than the biggest crater that it intersects? So please have a look at this image. I hope the poll's not hiding the middle part of the screen, which is a crucial part of where you need to look. You need to be looking around here for evidence. Is Calypso Rupes older than the biggest crater that it intersects? That's a yes/no answer to the poll. I can see poll results coming in here. More of you, okay, the yes and no's are running pretty neck and neck. Yes was ahead, but no is catching up. Okay, we've got the as I speak, we've got 92 people saying yes and 88 people saying no. A few more results creeping in. I guess somebody stopped the poll now. That's pretty good. So, in answer to the question, is it older? The yeses had it slightly. Actually, the answer is no, because you can see the thrust, the fault expression, just cutting through the crater here. So the fault has to be younger than that crater. So the answer was actually no, it's not older. But it was fairly evenly split. Pat yourselves on the back if you said no. But if you said yes, commiserate yourselves with the fact that you're in quite abundant company. I'm trying to move on to the next slide now. Here we go. I've zoomed in slightly. Hopefully you can see that this fault trace here cuts through that crater there. So that crater must have been in existence at least before this part of the fault moved. So the fault is younger than that bit of crater. This is a kind of logic which we use on the Earth. It's a cross-cutting relationship or a superposition relationship, and it's classic geology done on the Earth, and we apply it on other planets as well. We can do geology on other planets, and with space missions that send us images and other data of the quality we're getting now, we can act like terrestrial geologists on other bodies. And you'll be learning about this for Venus and in due course Mars. There's a lot of wonderful stuff coming out of Mars, of course, at the moment with the recent Mars landing from Perseverance. So Calypso Rupes is younger than this crater, and there's the evidence. And that is the end of my talk, and I've done 45 minutes, which is what I wanted to do. I've credited where the images come from here. They're from NASA, Johns Hopkins University, APL, and Carnegie Institute, Washington, because they were in charge of the Messenger spacecraft. And as Megan said at the start, the next talk is 22nd of April, which is a Thursday, about Venus, the next planet out from the sun. And that's by Peter Grindrod. And I'll be happy to take any questions now. Thank you for attending, and I will stop sharing my screen.
Thanks so much, Dave. That was absolutely wonderful. I couldn't stop gawking at all those incredible pictures that you were showing. They must take up a huge amount of space on your hard drive. We have loads and loads of questions here. I'm just going to try my very best to get through as many as possible. Sorry, I've got an echo. I'm just going to mute myself for 2 seconds. That should be better now. Okay, so the very first question I have is from somebody who submitted it anonymously. And it's, will we ever see a rover mission to Mercury? And there's a sort of follow-up question to that is, do you think we'll ever get some rock samples back from Mercury?
Okay. Well, there's certainly a study group forming looking at the feasibility of a lander to Mercury. I wonder if people would wonder, bearing in mind the extreme temperature range on Mercury, when would you land? What time of day would you land? And let people think about that before I answer it. But a static rover will come after a roving vehicle will be after we get a static lander. The next thing will be a static lander. A rover vehicle in due course, yes, and it's been suggested that because Mercury rotates so slowly, you could land and rove and keep pace with the sunrise, so you never got too hot. I mean, it's days twice as long as it's year, so you've got 176 days. So if you land at quite a high latitude, you can just move at the right time of day and keep the sun at the same part of the sky. Never get too hot, never get too cold. It will happen. It's not an immediate term. The time of day you would try to land with a static lander is just round about sunset. So you get a little bit of daylight, but it's begun to cool down. And then you keep your spacecraft heated with its batteries during the long night for doing your chemical analyses. But soon after sunrise, it's going to get so hot that you're not going to be able to keep your spacecraft cool enough to survive. So your Mercury lander, if it can't move, has got about 180 days of life before it will inevitably get too hot and will fry. So that's about missions to Mercury. What was the other half of the question? It
was in a sort of similar vein. Do you think we'll ever be able to get rock samples?
Oh, rock samples, of course. Well, it's so hard to get to Mercury. It's even harder to get back. So a space mission bringing rock samples back, tough. And that probably won't happen until we've had a rover on Mercury. So we're a long way down the line. We are hoping that there are some meteorites from Mercury somewhere. I forget whether Sarah Russell mentioned meteorites from the moon last month. We have meteorites known to have come from the moon and from Mars. But impacts on the moon and Mars throw debris to space. Rarely samples of that find their way to Earth. We've yet to recognize a meteorite that looks like it might have come from Mercury. But that's our best chance of getting hold of a piece of Mercury. A meteorite that's going to be about 3 to 3.5 billion years old, is rich in sulfur, low in iron, because Mercury's crustal rocks don't have much iron, but a lot of magnesium. That would say to us Mercury, because it wouldn't look like anything else we've got. And that will give us so much information about elements that we can't measure from orbit. But a meteorite from Mercury would be great to find, but we haven't found one yet.
So the best we can do is cross our fingers for someone to find one in the near future.
Yeah, well, we think a meteorite came down in the Cotswolds not many days ago. So who knows? It might be a bit of Mercury lying out somewhere near Stow-on-the-Wold if somebody could find it.
Brilliant. So the next question is from Luca, and Luca wants to know about the chemical composition of Mercury. So what kind of elements are there on Mercury? Are they similar to Earth, or is this kind of different?
Okay, well, of course, Mercury is made of the same elements as the Earth, but in different abundances. You don't go to space and find something which doesn't exist on the Earth. It's the same chemical elements. Okay, the crustal rocks, as I've just said, are high in magnesium, low in iron. We think they're probably 50 to 60% silicon. So those vast lava flows are not quite basalt, they're a bit richer in silica. They're high magnesium basalts, loosely speaking, to the geologists in the audience, but they've got more sulfur than we would expect. And we think Mercury was formed under chemically very reducing conditions. So despite having this very large iron core, not much iron has been incorporated in the rocky part of it. But it's recognizable rocks, as you'd find on the Earth or the Moon. Not that different. But if you're on the surface, you'd see mostly powdery regolith, like you do on the Moon. You leave a footprint almost everywhere on Mercury. There's not much solid rock. It's been pulverized by all the impacts.
Sure. Okay. So I've got a question here again from an anonymous submitter, and it's about the craters. So it's referring to the fact that craters, quite a few of the craters you showed look very much like lunar craters, or something we're familiar with seeing on the Moon. But how do the sort of the shape of these craters differ from lunar craters because of the difference in perhaps gravity that's in existence on Mercury?
Okay. Well, Mercury's gravity is twice as strong as the Moon, or 1/3 the strength of the Earth's gravity. So it does affect the crater forming process. An impact with the same energy hitting Mercury would form a slightly smaller crater than it would on the Moon, because the Moon's weaker gravity would let the debris travel a little bit further. But apart from that detail, the craters are pretty much identical. The small craters are bowl-shaped. As they get bigger, they have central peaks. Even bigger craters, that's from more energetic, faster or larger impactors, will have a ring of peaks in the middle, and really big impactors produce something like the Caloris Basin or the Imbrium Basin on the Moon. So the crater forming processes are pretty much independent of the nature of the surface material. Icy bodies, the moons of Saturn and Jupiter, which are icy, have craters looking very similar to lunar or Mercury craters. So the processes are much the same. It's only the details which differ.
Okay. So that comparison that person had sort of pulled out is, really valid in that.
Yeah, Mercury looks like the Moon, except for you don't get the strong contrast with the lunar lava plains are dark compared to the ancient rocks of the lunar highlands. On Mercury, it's all basalts without this flotation crust which the Moon has. That's something I didn't go into. There's a moon talk in this series, isn't there?
Yes,
People should go to that to find out about the Moon's primary crust and the lunar highlands. We don't have that on Mercury, but let me digress. After the impact that formed Mercury, the outer part of it would have been molten. That would have been a magma ocean. And all the crystals forming in that magma ocean sank to the bottom. None of them rose to the top, because it was low density, not rich enough in iron to be dense enough to cause the crystals to float. And that's denied Mercury the same kind of rock type we see on 3/4 of the lunar surface, which is these high albedo, light colored lunar highland rocks. Mercury didn't get them because it was too poor in iron.
That's brilliant. Thanks, Dave. So Paul's asked us if there are any places on Mercury that are in permanent darkness, and if this means that something like water or ice could exist in those places.
Yes, there are, Paul. Mercury's axis is almost exactly 90 degrees to its orbit, and craters at both poles have places where the sunlight never shines. So those are in permanent shadow. We don't think Mercury's axis is at all unstable, and these permanent shadows have been permanent shadows pretty much ever since those craters formed. And we do know that there is water ice inside some of these craters. We knew it we knew it 40 years ago from radar observations. You can see something in the Mercury's polar craters that reflects radar strongly as if it was water ice. And MESSENGER was able to peer into these craters with neutron spectrometers and find that it looked like there was a hydrogen-bearing substance down there, which tallies with water ice. And we think there is water ice and hydrocarbons sitting in these permanently shadowed regions, which are so cold that ice can survive there. So yes, we've got cold regions with ice near both of Mercury's poles.
Not
Who'd have thought it that close to the sun?
Yeah. So I guess kind of also similarly, Chris has asked us if Mercury has ever had an atmosphere.
No evidence of it. It depends what you call an atmosphere. It still today has what we call an exosphere. Mercury's atmosphere is 1,000 times denser than the Moon's atmosphere. That's 1,000 times almost nothing. it's billions of times less dense than the Earth's atmosphere. If you put a molecule of water vapor or oxygen, let it loose on Mercury, it will float away to space before it bumps into another atom. It's a surface-bounded exosphere. There is sodium and hydrogen and helium and magnesium atoms in near Mercury space, but they're not strongly held by the planet and they don't bounce into each other. They're not dense enough to bounce into each other. So you tend not to think of it as an atmosphere.
Okay, that's great. I've got somebody here that's curious about, I guess, some of the image processing or the colors that are used in the images. And the question is basically, are the lavas that you're showing really orange, or is that all down to image processing? And how much of that is, what's the exaggeration like on those?
It's very largely down to image processing. There is a standard exaggerated color product that the Messenger team produced. And things which look red in it are redder than the average. Things which look blue in it are bluer than the average. But if you or I were there, we'd be hard, with our own eyes, we'd be hard pushed to tell a difference. It's a very bland world, but you can do image processing to exaggerate the colors, and that does convey information. So it's a useful thing to do.
Okay. So Imogen wants to know why Mercury is cooling down.
All planets are cooling down because they were hot at their birth because of the violent collisions, and they generate heat internally by decay of radioactive elements, uranium, thorium, and potassium, are the big heat producing elements. But of course, those are declining in abundance with time because of half-lives. So there's less radioactive heat production as time goes by, and you're losing your primordial heat. So planetary bodies are cooling down very, very slowly because they insulate themselves, but they do cool down over time. The Earth's cooling down, but we don't see the thrust because of shrinking, because Earth's whole outer shell is being recycled all the time by plate tectonics. But it does exhibit itself really well on Mercury, where you haven't got these large-scale movements. All you can see is the slow shrinking. So it's very slow cooling because of loss of heat to space. It's losing slightly more heat than it's able to generate internally. Hope that
so you mentioned those, you mentioned those thrusts, and John's asked about the thrusts and the presence of thrusts on Mercury, and basically wondering whether the existence of thrust faults on Mercury implies that there is tectonic activity. And I was wondering if you could say a little bit more about the formation of those.
Okay, it's tectonic activity, which to me just means fracturing and moving of rock masses, but it's not plate tectonics. So I'm not sure what was behind the question. Plate tectonics on the Earth is because the rigid outer part, the crust and the upper mantle, which is what we call the lithosphere, moves relatively freely on the weaker part of the mantle that's below. And we've got new lithosphere forming at mid-ocean ridges, and we've got old stuff being subducted, like underneath the Andes at subduction zones. And that's a very, very large-scale process, which just goes on continually. On Mercury, all you've got is it's cooling down, and this bit gets pushed over that. And then it's done. It doesn't keep on going. Well, it does keep on going, but it's only built up to about 2 or 3 kilometers displacement over 3 billion years. I mean, the Pacific plate is going down below South America, or the floor of the Pacific Ocean is going down below South America at 10 centimeters a year or something, which is an enormous rate compared to the movements we see on Mercury. So it's very different kind of tectonic motion on Mercury than what we see on the Earth.
No, that's really interesting and easily confused, I think.
Because of the word tectonic. You've got to look for plate to go with tectonic. Plate tectonics on the Earth, plate tectonics nowhere else in the solar system that we're convinced of. Pete Grindrod might have some views about whether it's ever happened on Venus. Listen out for that.
So some of the early images used in your talk show really bright straight lines on the surface of Mercury, and someone wants to know if these are impact ejecta that we sometimes see on the moon. You might want to explain what impact ejecta are as well.
Yeah, I think we're referring to rays from impact craters. I'm just going to share the screen. and show that. Come on, share. It's not sharing, is it?
Not quite yet. It might just take a second.
It doesn't look like it wants to share. I'm not sure. Okay, sorry about that. It doesn't seem to want to share. Yeah, there are there are straight lines going across the whole hemispheres, which radiate out from some of the youngest craters. We see these on the moon as well. If you look at the moon near full moon with binoculars, you can see ejecta rays. So a young crater draws attention to itself because when the sun is overhead, the fragmentary ejecta which radiates away forms these bright ray-like features, and those indeed are visible on Mercury. And that's what, was it Paul had seen. It's not going to let me share, but it's sharing
it's
now,
just started.
isn't it?
Yeah.
Okay. Well, this view I had at the end, it's just being really slow. There's a crater here with these streaks running out from it. There's a crater here with streaks running out from it. Those are ejecta rays. Okay, there we go. I think we're looking at features like this one.
Yeah, you can see them really
There's
clearly.
a young crater there, and there's another young crater there. And if I was to show you the global rotating view, which I won't attempt to do now, you'd see many more. So yeah, Mercury's young craters do have these ejecta rays, very much like we see on the moon. Well spotted.
That's awesome. Listen, we have about double as many as questions that we've just gone through to ask you, and I don't think we'll ever get to the end. So I think I'm going to choose one last question to finish up from, and it's from Ria, who's asked us, in your opinion, what's the most exciting thing about Mercury?
I'm going to answer two things. I'm a volcanologist, so I love these explosive volcanoes. I didn't expect to see those. They fascinate me. We've got a couple of papers just accepted to be published about these. David Pegger, a recent PhD student of mine. So explosive volcanism is great to find. That's because I'm a selfish volcanologist and I like to see volcanoes. The bigger question about Mercury that would excite more people is kind of related to that. It's that Mercury is rich in these volatile elements. I've mentioned 2 to 4% sulfur wherever you look. I've mentioned we've got explosive volcanism, which requires stuff which can get turned to gas and escape violently from eruptions. I've mentioned the hollows, the substances which are breaking apart and escaping to space must somehow be volatile. We've also got measurements from some of Messenger's geochemical instruments about chlorine and other volatile elements. It doesn't fit. It should not be like that. This is part of it being the problem child of the solar system. It is weird. It didn't ought to be like that. And we hope we can understand why soon.
And there's something quite fascinating about that weirdness. So absolutely, totally get where you're coming from. Thanks, Dave. There's floods and floods of messages pouring in from the many attendees we've had both on YouTube and Zoom. Thanks to everybody for coming along. As Dave just mentioned really recently, we do have a whole series of these lectures, so please do look at our website. There's a Year of Space events page where they're all listed, and sign up to come to as many as you're able to. They'll also be put on our YouTube for posterity, so you can come back and watch in your own time, and again, if you like. Thanks very much again, Dave, and we hope to see everybody soon. Take care.
Thanks, everybody.